Welcome to Science Notebook. Today, we're exploring a technology that could literally change everything about the world we live in.
In the world of physics, there's this one discovery. It gets people even more excited than fusion energy or quantum computers. It's often called the Holy Grail. So, what exactly is it?
Well, that would be a room-temperature superconductor, or RTSC for short. And what it is a material that can conduct electricity with absolutely zero resistance at just normal everyday temperatures. And believe me, this isn't just some small step forward. We're talking about a revolutionary leap.
So here's our roadmap for how this single breakthrough could completely reshape our world. First, we'll look at how it could erase a universal tax on energy. Then we'll get into unlocking fusion and frictionless travel. After that, a new age of computing, how it could put advanced healthcare right in your hand. And finally, how the future could begin, well, right now.
First up, erasing the universal tax. Now, to really get why this is such a big deal, we have to understand the invisible enemy our entire modern world is constantly fighting against: electrical resistance.
You see, every single time we use electricity, whether it's to power our lights or charge our phones, we're paying this invisible energy tax. It's this unavoidable fee that's just baked into modern life.
So how big is that tax? Somewhere between 5 and 10%. Think about that for a second. That's the amount of all the electricity generated on the entire planet that is simply lost. It just vanishes, wasted as heat, while it travels through our power lines.
And the difference this would make is just stark. Today's grid has significant energy loss and its range is pretty limited. But with an RTST power grid, we'd have zero energy loss. Zero. We could transmit power from a solar farm in the Sahara all the way to a city in Europe with no waste at all. Our global energy grid would become nearly 100% efficient, practically overnight.
Okay, now let's see how getting rid of all that resistance unlocks two technologies that sound like they're straight out of science fiction: fusion energy and frictionless travel.
So here's the thing. Superconductors are the absolute key to making nuclear fusion work. Problem is, today's reactors need these massive, incredibly fragile magnets that have to be cooled with tons of liquid helium. The RTSC solution, though, would let us build smaller, way cheaper, and much more robust tabletop fusion reactors. And the impact here is just staggering. Clean, limitless fusion energy stops being a distant dream and becomes a near-term reality.
That's energy, pretty much solved. But what about how we get around? What about transportation? Just try for a moment to imagine a world without any friction.
I mean, sure, we already have magnetic levitation or Maglev trains, but they're super rare and incredibly expensive, all because of those crazy cooling needs. Well, the RTSC revolution just changes the whole game. We're talking about frictionless trains zipping along at over 500 miles per hour. Your own personal car could just hover above magnetic roads. That means no more tire wear and a whole lot fewer accidents. It's wild.
Okay, let's move on. Let's look at how RTSCs could affect the very device you're probably watching this on right now. We're talking about a new age of computing, one that goes way beyond the limits of Moore's law. Let me ask you a simple question. Why does your laptop get hot? Or your phone, for that matter?
Yep, the answer, once again, is resistance. When electrons move through those silicon chips, they collide and generate heat. This is the exact reason massive data centers need billions of gallons of water just for cooling. Heat, that's the fundamental bottleneck of modern computing.
But with RTSC computer chips, you'd have zero resistance, which means zero heat. The impact of that? We could pack transistors 1,000 times more densely on a chip without them melting. This would trigger a second Moore's law, making today's fastest supercomputers look like simple pocket calculators.
And this technology won't just make things faster. It's going to make life-saving technology accessible to everyone on the planet.
Just take an MRI machine. Today, they cost millions, they need a huge room, and they use these giant vats of liquid helium to cool their superconducting magnets. An RTSC-powered MRI, on the other hand, could be inexpensive, common, and about the size of a handheld tablet, with no special cooling needed at all.
Let that sink in for a second. What that really means: life-saving diagnostic imaging could become as cheap and as common as a digital thermometer. You could have one available in every rural clinic, maybe even in every single household worldwide.
So, this brings us to our final section. It's so important to understand why the phrase room temperature is the most critical part of this entire discovery. This is really about how we get this technology out of the lab and into your pocket.
You see, for over a century, superconductivity only happened near absolute zero, at 4 Kelvin. That's about minus 452 degrees Fahrenheit.
The discovery of high-temperature superconductors that work at 77 Kelvin, a balmy -321 Fahrenheit, was already considered totally mind-blowing. But a room-temperature superconductor works at around 293 Kelvin, room temperature. This is the monumental leap we are talking about.
That right there, that is the bridge. It's the bridge between laboratory physics and universal application. It means these incredible materials can finally work in your hand, in your car, and in your pocket without any specialized, expensive cooling equipment at all.
To put all of this into perspective, I want to leave you with this final thought. We aren't just looking for a new metal. We are looking for the key to a Type 1 civilization, and that's a civilization that can harness all the energy available on its planet. The moment we stop fighting resistance is the moment the future truly begins. So I'll just leave you with this question. What would you build first?